Question 3 then is the fat question. And the first thing it asks you is about this particular fat, what might make you think that it might have been obtained from processed food rather than from sort of raw, fresh food. And the answer is it's this trans double bond there. So what you need to know is that when you have unsaturated fats, remember unsaturated means it contains double bonds, polyunsaturated means it contains several double bonds, but when you have those, most commonly they're cis double bonds, where the carbon chain comes in, forms a double bond, and then leaves on the same side. So that one's trans, because it's coming in and leaving on opposite sides. And those are rare in nature, but they're formed when you are trying to hydrogenate fat. So if you're trying to add hydrogen to reduce the number of double bonds, which is what you do, for example, when you make margarine, as a side reaction in that process, you tend to isomerize cis bonds to trans bonds. Okay, so the answer is that the presence of the trans carbon-carbon double bond suggests it might be produced from processed food because those are rare in nature, but they're produced during hydrogenation. Secondly, what's the problem if you eat lots of this? Again, it's the trans double bond that's the issue. So trans fats are what these sort of compounds are called. So triglycerides containing trans double bonds, if you eat them, they lead to an elevated concentration of bad cholesterol in the blood. So all you have to call it, you don't have to know what bad cholesterol is, but it increases the concentration of bad cholesterol, and that can lead to coronary heart disease and stroke. Okay, third thing is alkaline hydrolysis is the answer to the next question. The reaction with aqueous sodium hydroxide is alkaline hydrolysis, and what it does is it breaks these ester linkages here. Okay, so hopefully you recognise that that's an ester bond. COO in the middle of a molecule is an ester, and like any esters, you can hydrolyze them by reaction with either aqueous acid or aqueous alkali. In this case, it's aqueous alkali, and what that means is that you react with 3 moles of OH minus. Okay, so 1 mole of OH minus for each mole of ester bonds that you've got to break, and the product of that is that you get glycerol, which is this. Okay, so that's the alcohol half of the ester group is restored to being OH, so you get glycerol, which is that, and the carboxylic acid part, because it's under aldehyde conditions, you don't get the carboxylic acid, you get the negative ion, like that, so you get COO minus. If you like, you can put the Na plus in there as well, because it's sodium hydroxide, but the important thing is that you get those negative ions. So this is product P, the carboxylate ion, and the next question asks you about converting that to product R by neutralization. So that's extremely simple, so if we just get rid of the rest of this from here, we can focus on just one of those molecules of P, and it's very simple. We're simply taking this, which is the conjugate base of a weak acid, and we're adding protons to it, and that means it will pick them up and restore the acid. So all it does is that reacts with H plus, aqueous, and you get exactly the same thing. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 15, 16, COOH, and that's all there is to it. Is that the right place? 1, 2, yeah, that's right. Okay, so that's the reaction. Just that reacts with H plus ions from the acid to restore the parent fatty acid. Now we've got to do the shorthand description of this fatty acid that we've created. So remember, the way it works is, first of all, you count the total number of carbons in the chain, which is 16. So it's 16. And then you list the number of double bonds, which is 1. And for each of those double bonds, you put in brackets the number of the carbon where it starts. So in this case, there is only 1, and it starts at carbon. Remember, that's carbon 1, the COOH, so it's 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's 16, 1, bracket 9. And for completeness, you could put the trans in front of it to specify the geometry of the double bond. Final question says, if you take that unsaturated carboxylic acid, you can turn it into a polymer. So for this, we're just thinking of it basically as an alkene, because you've got the alkene group in the middle, and like any other alkene, you can do addition polymerization on it. So to get the repeat unit, remember a repeat unit of an alkene polymer always looks like that. And what you put on these four corners are the four things surrounding the two carbons of the double bond. So for this carbon, which will be that one, we've got this chain of 1, 2, 3, 4, 5, 6. So we get 1, 2, 3, 4, 5, 6 there, and a hydrogen. And for this carbon, we've got a hydrogen, and then this chain of 1, 2, 3, 4, 5, 6, 7, 8, terminating in the carboxylic acid. So that's 1, 2, 3, 4, 5, 6, 7, 8, with COOH at the end. And it asks for 2 repeat units, so you just draw the same thing again, connected up, like that. Make sure you've got the bond between those two carbons, and you just draw the same thing again. 1, 2, 3, 4, 5, 6, and a hydrogen, and then 1, 2, 3, 4, 5, 6, 7, 8, with the last one being COOH. And usually that's all you need. You can, if you like, put the whole thing in a bracket, but if you do that, make sure that the bond at the end goes all the way out through to the other side of the bracket, like that, and like that. And that's it for the repeat unit. And that's the end of question 3.